Hey everybody, it's Ripley back again. All right, before we get into the teeth of this specific lesson, I really want to talk to everybody about what we're doing as we work our way through these techniques of integration. I'm handing you tools, and all of the tools end up in the toolbox. Now, the first and most important tool is just an antiderivative. Have I memorized an antiderivative? Have I memorized an antiderivative? So, for example, if I say, okay, I'm going to take the indefinite integral of cosine of x dx, you better be able to look at that and say, okay, that's easy. That's sine of x plus c, because I memorized the fact that the antiderivative of cosine is sine. More importantly, I've memorized the fact that the derivative of sine is cosine of x. The second is, and it's the most important, biggest, hardest hitting tool, and that, of course, is substitution. After that, we go through algebra. Now, these two are going to be kind of interchangeable, aren't they? Algebra, because sometimes I can just do a simple algebraic technique. You remember like x plus 1 over the square root of x dx, and I do a little bit of algebra, and this thing turns into the square root of x plus 1 over root x dx. And this is easy. This is 2/3 x to the 3/2, because I've memorized the antiderivatives of x to the n, right? And this is plus 2 root x, the one I told you to memorize, and then of course plus c. Now we started getting even more specialized. This was an esoteric rule, but it turns, or excuse me, tool, but it turns up a lot, and that's of course parts, right? The integral of u dv is equal to uv minus the integral of v du. That was a biggie. That gave us like the integral of the natural log of x dx, which turns of course into x ln x minus x plus c. That's a biggie. All right, we use it. We don't use it a ton, and we don't want to use it if we don't have to, because it's a lot of work. However, when we need it, it's a really good specialized tool. Trigonometric integration is similar in that respect. Now, before we start into trigonometric integration, where we're actually using tricks, I just want to make sure that everybody knows the antiderivatives of all of the main trigs. I know the antiderivative of sine of x is negative cosine of x plus c. The antiderivative of cosine of x, which as we spoke about before, is sine of x plus c. Those are the biggies, right? The antiderivative of tangent of x is what? Is negative the natural log, the absolute value of cosine of x plus c, or the positive natural log of the secant of x plus c, right? Because I can lift this -1 up to an exponent. All right, now, if you recall, we can use substitution to figure out what the antiderivative of the secant of x is. This becomes, if I multiply top and bottom by secant of x plus tangent of x, which is just multiplying by a goofy looking 1, I end up with the natural log of the absolute value of secant x plus tangent of x plus c. If these are the biggies, what else am I missing here? I'm missing cotan. Whoops, cotan of x dx is equal to the negative natural log of the absolute value of the cosecant of x plus cotan of x plus c. That negative comes from the fact that when I multiply through by cosecant x, cotan x, and I take the derivative, I end up with negatives. And last but not least, whoops, that's not cotan, that's cosecant. Don't listen to Ripley. That boy's crazy. Sorry about that, you guys. This is cosecant of x. Try that again. All right, now cotan of x dx is equal to the natural log of the absolute value of sine of x plus c, or I could write it as the negative natural log of the absolute value of cosecant x plus c, but that's just a little bit silly. Okay, so know your 6 antiderivatives of the main 6 trig functions. You have to. Again, it's the vocab. If you don't memorize them, if you don't throw them on a flashcard, if you don't practice with them once a week, then you're going to be in the weeds and you're going to suffer unduly, and I don't want you to do that. Okay, so let's get into something a little more fun. For example, what if I were to say, what is the antiderivative of sine x cosine of x dx? Excuse me. Now, that's pretty easy, right? That's not so bad. We would just do a u substitution, right? I'd let u equal sine of x. I'd let du equals cos x dx. And then this guy would turn into the integral of u du, right? Which is just u squared halves plus c, or sine squared x over 2 plus c, and I'd be done. However, what would happen if, say, I did this? What if I did sine cubed of x times the cosine of x? Okay? Now what happens? Well, let's go cosine of x dx. Well, there's a hint here. There's a super sweet, nice little hint, and it's this odd power right here, okay? Now, what that enables me to do when I see that odd power, it's a hint. It doesn't work every single time. What I'm about to show you is not an end-all, be-all of all the tools, but what it does give me is it gives me a nice little move, and I'm going to show you what that move is. It enables me to write this instead of sine cubed x, I can write this as sine squared x, cosine of x, sine of x. I can scrape off one of the signs. Now, had this been cos to the fifth instead of sine cubed, I could do exactly the same thing. I could scrape off an extra cos. Now, why did I do that? Well, the reason I did is because I know that sine squared x is just what? It's 1 minus cos squared. So this can be written as the integral of 1 minus cos squared x times the cosine of x times the sine of x dx. Now, what does that help with, you may ask? Well, look close. This is very close to the derivative of this and these guys, right? So if I let u equal the cosine of x, I take care of that one and that one. Now you may be like, wait, does that help? I just said wait. There's a quarter. It might. Let's see. Let's check it out. Let's swing a pinata stick and see what happens. I end up with a negative sine of x. Dang, I want a positive sine of x. That doesn't scare me. And there's my dx. So negative du is equal to sine of x dx. Okay, cool. Let's see what happens. Negative out in front. I get 1 minus u squared, because u is cosine of x, times u du. Hey, wait a sec. This is just negative the integral of u minus u cubed du. That's just an antiderivative one, right? So negative quantity u squared halves minus u to the fourths plus c. And then we clean everything up. I'm going to distribute the negative through just because it'll make me happy, right? And I end up with what? U to the fourth, but that's really cosine to the fourth x over 4 minus cosine squared x over 2 plus c. Isn't that cool? Remember, these guys switched places because this guy was out in front. All right, now take a gander. If I wanted to, I could take the derivative. I really don't want to take the derivative. It would take a really long time, and there'd be chain rules and product rules, but you might be able to see kind of where this thing is going to go, okay? And you can tell that I have the correct answer. Now, let me give you another example. Let's do something that's a little bit more fun. How about the integral of cosine squared x dx? Now, that's trig. This is a trig integram right there. It's just trig, nothing to it. And you may say, wait a sec, Ripley, there's no sign hanging off. I can't do a quick and easy use substitution. There's no sign. But wait a sec, don't I remember? Let's change the colors on these guys real quick, because I'll use the same colored pen I use if you guys don't remember these. Remember that cosine squared of x from back in pre-calc, back in trig actually, is 1 plus cosine of 2x all over 2. Sine squared x, and I would put these on your note card, on your cheat sheet, on the thing that you're going to use to remember these types of things, is just 1 minus cosine of 2x all over 2. These both come from the fact that sine squared x plus cos squared x is equal to 1, and cos squared x minus, there should be an x in there, minus sine squared x is equal to cosine of 2x. If I subtract, my cos squareds disappear, right? And I end up with 1 minus cos 2x divided by 2, which gives me my sine squared. If I add them, my sine squareds disappear. And then I divide by 2, and that's where I get this. So I can use that fact to turn this into something that's delightful. This is the integral of 1 plus cos 2x. The whole thing, the whole thing over 2 dx. Now, I am simple country folk, but I can definitely turn this into the integral of 1/2 plus cosine of 2x. Ooh, that's a linear term. Those are easy to do. Over 2 dx. And this just turns into x over 2 plus sine of 2x over 4 plus c. Remember the antiderivative, it's got a linear term. I'm not going to do a u substitution because it's too easy. All right? Okay, now, that's pretty simple. Let's do one more kind of god-awful monstrosity nasty thing. How about the integral of tangent to the 5th of x, and then I'm going to do secant to the 7th of x dx. That looks absolutely horrific. Okay, well, what do you think? Let's look close. One thing that I could do is well, they both have an odd number. They both have an odd exponent, and that's a big hint. Wait a sec. Is there a function, so I'm just going to do this kind of parenthetically over here. Is there a function whose derivative is secant x tangent of x? Because you may say, well, Ripley, why don't we let u equal secant or equal tangent of x? Because then the derivative is secant squared. Yeah, but I'm going to have this thing hanging off, right? Isn't the derivative of secant x tangent x? And I have scraped off these odd powers. So let's see what this looks like. This turns into tangent to the 4th x, secant to the 6th x. Now that looks intimidating, but let's not be afraid for a minute. This is secant of x, tangent of x. That was the one that I scraped off to make these even. Dx, you're probably seeing where this is going. If this is the derivative of secant of x, then I need to turn this entire integrand, not including this guy, into secants, right? Well, we're not afraid. What's our Pythagorean identity? Don't I know, let's change colors again. Excuse me. Don't I know that tangent squared x plus 1 is equal to secant squared x? Where did we get that? Well, we got it from sine squared plus cos squared equals 1. If I divide everything through by cos squared, I get sine squared over cos squared, tangent squared, whoop, cos squared over cos squared, 1, haha, and 1 over cos squared, secant squared, blah, blah, and that's where I'm at. So I know that this guy, I know that tangent squared x is equal to secant squared x minus 1. So I'm going to leave the color of my pen changed. So this becomes the integral of, well, it's going to be this guy is tan squared, but squared. So I get secant squared x minus 1 squared times secant to the 6th x times secant x tangent x. Now it's really tempting, don't forget your dx, it's really tempting to stuff that secant x back in there, right? Because you're like, oh, everything needs to be secant. Well, no, it doesn't. Remember, I need to leave out a secant x tangent x because I know it's the derivative of secant. So now here's the sweet spot. Here's where I get to go back and say, let's let u equal secant x. Now you got to be careful here because this can get really confusing if you're not careful. I know that du is equal to secant x tangent x. Now this is my du. That secant and those secants and those secants they live in my u. The du is gobbled up over here. So this becomes the integral of u squared minus 1 squared times u to the 6th du. Now, I should probably take the time to do a little algebra. Remember, algebra was one of our main tools. So let's look at this. This becomes u to the 4th minus 2u squared plus 1 times u to the 6th du. This becomes, what? U to the 10th minus 2u to the 8th. That's an equals, by the way, not a minus. Plus u to the 6th. What's going on here? I'm forgetting all my stuff. There's my integral. And there's my du. So this becomes u to the 11th divided by 11 minus 2u to the 9th divided by 9 plus u to the 7 sevenths plus c. And then I just back substitute. Now it's a god-awful integral, isn't it? It's terrible. I mean, look at what this turns into. It turns into secant to the 11th of x over 11 minus 2/9 secant to the 7th of x, that's a 9, isn't it? Not a 7th, plus secant to the 7th of x, 7ths, plus c. And I'm done. Not exactly an intuitive solution to that thing, is it? Kind of crazy. Okay, cool. Now, let me give you one other thing, because this can be a little bit juicy from time to time, and you may have forgotten this from your trig from back in the day. If you remember product to sum, and then you can run this backwards. I'll do it parenthetically, sum to product from pre-calc. I guess for most of you that would be last year. What you should remember is that the sine of A, cosine of B, and truthfully, I have to look these up very often, but I can build them also from the sum formula. This becomes 1/2 times, and this is going to be sine of A minus B. I always have to look at, sine of A minus B. I don't know where I got that extra parenthesis from. Plus sine of A plus B. That's this guy. Now, if I have sine of A, sine of B, you can probably see where a lot of these come from. This is equal to 1/2 times, this is cosine of A minus B plus, minus cosine of A plus B, cosine of A plus B. So notice what we're checking off here. And then last but not least, if I have cosine of A, cosine of B, this is equal to 1/2. This guy turns into the cosine of A minus B plus cosine of A plus B. And what this gives you the ability to do, if you recall where these come from back in the day, these are sum to product rules, right? You could use you could use these formulas to show that this is true. Remember, sine of alpha plus beta is sine alpha sine beta plus, or sine alpha cos beta plus sine beta cos alpha, et cetera, et cetera. We memorized those back in pre-calculus. All right, so what does this help us do? This helps us do an integral of something like, let's do the sine of 3x cosine of 4x. Now watch what happens. Now again, this is a super esoteric tool, but like most esoteric tools, you don't appreciate how important it is and how useful it is until you need it. Now watch what happens. This becomes the integral of 1/2, and then we're going to do what? We're going to go whoop, and we're going to go sine of A minus B, right? So this is going to be the sine of negative x. Since sine is odd, we can pull that negative out, plus the sine of A plus B, right? So this becomes the sine of 7x. That's this guy. And then we've got dx. Now, I'm going to take just a minute. I'm going to pull my 1/2 out. Let's pull well, should we do the negative? Yeah, let's just write it this way. Let's go sine of 7x minus sine of x dx, and watch what happens. This is going to become what? 1/14 the cosine of 7x. Don't forget our negative, right? Because the antiderivative sign is negative cos. Minus, what do we have here? Or plus cosine of x over 2 plus c. Now, this is one of those that we could actually double check by taking a derivative really quickly. The derivative of cosine of 7x is negative sine of 7x times 7. That would cancel and give you 1/2 sine of 7x. The derivative of cosine of x over 2 is just negative sine of x over 2. And we're good. All right. So you've got the tools. You've got this special tool. All right. Remember, though, this is a special tool. You want to exhaust all the other tools before you get to this one if you don't absolutely need it. Okay? All right. I'm done for the day. I look forward to seeing you guys in class. Have a wonderful day. Talk to you soon.